So let's be an n-dimensional vector space, and also we let be a base, ordered basis for 50. And now we know for each vector in the vector space V, that is unique representation for X as a linear combination of basis vectors V. So X actually is equal to 1 1 plus 2 Okay, so we have a unique representation, means that the coefficients alpha 1 up to alpha n are determined uniquely by vectors. And we call so we group the coefficient together into a vector, right? And this vector with this notation is called the coordinate vector relative to the basis. And for convenience, B coordinate. Okay. So sometimes we just explicitly denote the coordinate vector with the B dash. Okay? So B dash coordinate vector. And sometimes we omit the vector. Let's say B coordinate. Right. Later, we may need to consider another ordered basis, C So very soon we may consider more than one basis for the same n-dimensional vector space. So we would like to know the relation between the big coordinate and the big coordinate. Right, so now recall that the coordinate vector assignment isomorphism. Okay, move that forward, right? So that is a linear transformation from the n-dimensional vector space region to the n-dimensional Euclidean space. And this linear transformation is bijective, means that it is much wider out. Right? So we prove that. So this is. So now, so this is true for any ordered basis, right? Now, with x equal to summation alpha I in time. Okay? Maybe I say with so if we know the big coordinate of the vector x, we know that that means that x can be written as the linear combination of the basis vectors in B, right? And the coefficient is in the B coordinates. From the definition we just mentioned. Right? Okay, so now we apply the coordinate of transformation. And then, and by applying this time, try to take the C coordinate, right? On both sides. So we have now equal to summation okay. So now we take the C coordinate on both sides. And because taking the C coordinate, this action is a linear transformation. So we have, so by linearity, bilinearity of this transformation. Okay, any questions up here? All right, so now, vector X is in a vector space V. So V can be arbitrary, right? Can be the set of polynomials, can be the set of sequences, set of functions, a lot of things. But now, we have the representation by using what? By using column vectors. Because coordinate vectors are column vectors in the n-dimensional Euclidean space. Okay, so now we have rewrite now we can have x equal to okay, so you can write this equation into a matrix equation. The advantage is that, what is this column vector? The column vector is just the b coordinates of x. Alright, so we can write p so I will use that and here is so I take this notation. Okay, so this matrix will be denoted as where the n-dimensional matrix. Transition from coordinate so C coordinate. Alright, so I use this notation. So now it becomes too reasonable to get the C coordinate of a vector x in a vector space V. What we do is that, first of all, we have a coordinate, find out a B coordinate, and then we use the coordinate transition. Right? So this is a transition matrix from the B coordinate system to the C coordinate system. So back here. So the notation, I want this notation tells you some story. Okay. It's easy to memorize, right? Yes, please. Span. Yeah. Well, actually, coordinate system. To have a coordinate system means that we have, first of all, we could choose a basis. So now, for a basis, we have two things. The first thing is that this basis spans the whole vector space. So spanning is just one of its functions. The second thing is that this basis should be a linearly independent. Yeah, yes, spanning, yes. B span B, yes. But not enough. B should also a linearly independent. So with the basis, we can establish a coordinate system. Okay? So we have for every vector in capital V in the vector space, we have a coordinate vector. So that means that we establish a coordinate system for V. Because every vector can be represented by a coordinate vector. And any coordinate vector is just a vector in n-dimensional linear space. So, did I answer your question? Or you may have other questions. Okay? Yeah, you can raise other questions here. Okay, so here, so you can see that what is the transition matrix? The transition matrix is constructed column by column because it's an n times n matrix. So it consists of n columns. Okay, each column is a column vectors in n, right? And the first column is actually the first basis vector in B, but in the C coordinate system. Okay? And the second column is the second basis vector in B, okay, in B, but you take the C coordinate, etc. Right? So the building up of this transition matrix is quite spatial. Right? It's quite spatial because you should use the basis vector in the order basis, but you should take the C coordinate for each basis vector. Right? So that is the due process. Okay. Okay. When you want to construct such a transition matrix. Right, so we can state a theorem. Right, so instead we call the change of coordinate system. Okay, so given two ordered bases B and C for finite dimensional. Vector space V B coordinate. And the C coordinate. Of a vector V are related where is the transition matrix. And that's a matrix. So we know how to do the change of coordinates. You know. You mark. It's an isomorphism from okay? Why? Why it is an isomorphism? So if we want to give a curve, now here is one. We know So this is an isomorphism. This is also another isomorphism. Okay. Now the composition. So that inverse. Isomorphism. Right? So this inverse is isomorphism. Okay? And now, sorry, I use B. Okay, I will. So the inverse of this isomorphism is also an isomorphism. Okay, so now the composition. The composition is that you go from Rn right to V, so you have Rn to Rn. It's an isomorphism. Because we proved that the composition of two isomorphisms is also an isomorphism. Okay, and so this is the we'll go to So from the B coordinate to the C coordinate, right? We establish an isomorphism. Okay? Okay, so the change from the B coordinate system to C coordinate system. All right. And we also we have just I see. Okay. I think I have to say that the change. Okay, there's a change. We have just shown that is the matrix representation of the isomorphism. Okay, so it's just a matrix representation. But I have to say the change, so I have to say the goes to C. Because with the bracket means the yeah. Maybe it's more clear in that. Okay, so the change from B coordinate system to C coordinate, the change from this coordinate vector to C coordinate vector, and okay, so it's just yeah, it's clear. So this composition, right, actually it is doing the coordinate change. Okay, so what we have done here is to show that this transition matrix is the metric representation of such an isomorphic. Because coordinate change is an isomorphism. Any questions? Remember here we have x, right, goes to the B coordinate. And here is x go to C coordinate. And the inverse of this coordinate function is that we have it goes back to x. Right? So the composition is that we start from the B coordinate vector, and we synthesize into the x itself. Just as the proof, I just erased it. Okay. So I just because that how do we recover x from the coordinate vector? Well, the recovery is that this is just alpha 1 v1 plus alpha 2 v2. Right? So the coefficients is contained here, right? Because this is okay. The coordinate vector. So from the coordinate vector, we know the coefficients. So we use the coefficient to synthesis back x. Okay, and then use we have x here, right? And use the C coordinate to get the C coordinate. So that is the process. I just demonstrate that because all these transforms are isomorphisms. Right? The point is they are all isomorphisms. So the compositions becomes to isomorphism. So they are all linear. They are all linear. And what we compute in the theorem here, this transition matrix is actually the metric representation of the isomorphism. Any questions? Okay, so now the next thing So the next question is, what? If we want to know the transition matrix, right, from the C coordinate system to P coordinate, so what is that? Okay, since we know that so if we exchange the row of B and C, so we have this one, right? And and the reason why I have to make a remark is because this transition matrix is a matrix representation of an isomorphic. So this matrix must be invertible. Okay? So the inverse of this matrix, this transition matrix is this. Right. And from here, we know that if we take the inverse, so okay, so that right. So when we multiply the inverse of this transition matrix, you get this one. Right? So you compare them, we have the change from C coordinate system to P coordinate system. This transition matrix is the same, is the inverse of the transition matrix, okay, from the B coordinate system to C coordinate system. So the answer is easy, right? It's just like this. So everything is quite natural, right? Especially I use this language, this notation. Right. Now, so this is for a vector space. Now we consider a linear transformation from a vector from an n-dimensional vector space V, Q, and n-dimensional vector space. Right. So V is the domain of the linear transformation of T. Got to put T. The linear transform T, the domain V is n-dimensional, and the codomain W is n-dimensional. So we consider such a linear transformation. All right. So let's B. And the C basis. We also relate from W 1, 2, and from probably so order W. Oh, not yet. I think too much at this step. So that's why. But okay. So maybe I don't need this. So let B be all the basis for B and C. And all the basis for W. Okay. I think is that I use this. I will get trouble. I will get trouble, yeah. So I just change. No. Sorry, I know because I foresee something. All right, but I hope you will not be get confused. Because in here, B and C are two bases for the same vector space, right? For V. But now I change a little bit. The B basis is for V, and the C basis is for W. So they serve spaces for different vector space. Is that okay for you? Just change. You will turn to the next page, okay? Temporarily forget the previous page. Is that okay for you? I'm a little bit worried about you still have a very good memory because I have short memory. I forget everything very soon. But you are very young, so you can memorize things very long time. So I ask you to temporarily forget the things here. Okay, so I just changed it. It's much more easier for me to deal with it. All right. So now, in the vector space V, I establish a B coordinate system. In the vector space W, I establish a C coordinate system. Okay, that is what I want. Okay, good. So now for all x into V, right? And with now with the B coordinate vector, we have you can synthesize the vector back, right? By the coordinate. So So we have this one. I, right? And 3i. Okay? So we can synthesis by using this inverse. That's more bigger, right? Okay. Then dx, right, is equal to summation now, and by applying the C-coordinate system on both sides, because that the C-coordinate system is for the codomain W, right? The codomain W. So that dx on the system, it comes to, so once again, because the taking coordinates is isomorphism, it's linear, so we have that. See here. Okay, and so that this is, so we can write down by a matrix. All right, so we have you see so the image of the vector in the C-coordinate system, because the image is in W, and we create C-coordinate system for the codomain W, right? So this is the C-coordinate vector of the image of X is equal to a matrix times the B-coordinate of X, right? And this matrix we will be denoted as the linear transformation relative to basis B for V, basis C for W. Alright? C. Right, So the construction of this matrix, is that for each basis vector in B, right? Then you take its image in W, and then take the C coordinate. For the second basis vector in B, you take its image, and then take the C coordinate, etc. So what is this? It's an M trans M matrix. Okay? Because it has n columns. But each column is coordinate vector. And in Rm, okay? So it's an M times M matrix. And it's called the matrix representation of T relative to the basis E for V and the basis C for so that's why we use B and C. So this matrix representation depends on the basis you choose for domain B, as well as the basis C you choose for the codomain W. If you use different B or different C, then you will get different matrix representation. Right. So now this is for linear transformation. So we talked this before, right? Talked about this in I think in chapter 2. Okay. So in chapter 2, we mentioned linear transformation from an arbitrary vector space to arbitrary vector space. Okay. And we talk about the matrix representation for the linear transformation. Here is more specific. Here that the matrix representation depends on the coordinate system we choose for the domain and for the codomain. If you change the coordinate system, you will change the matrix representation. Okay, so that is the basic thing. Any questions? Alright, so next question. What is the relation of E, C, between So it's possible that you choose different bases for B and different bases C prime for W. So now, relative to the new basis B prime and new basis C prime, you have a different matrix representation. Okay? Now, what is the relation between these two matrix representations? Okay. All right, so let me draw the diagram. Everything just linear transformation. right? So we start with P. So we know P here, and so we have X. So we go to P, right? So this is a linear transformation. Okay. Now coordinate. What is that? V goes to Rn. Okay. So X goes to right. And with beta prime, we have N and X goes to. So when we use different bases for B, we have this isomorphism. Okay. Now for C, this is Rm. So we have Y goes to Y, C prime, which is from W, goes to Rm. So it's Y goes to Y, C. Alright, so now we have 5. So this one is just linear transformation, but the rest 4 are isomorphisms. So now, the thing is that what is this metric representation? How do we get it? So what is that? But we can, so we think about R, and we go to V, we go to W, and then go to Rm. Alright, so this is the case we got. So from here, we have the V, right, go to X, by synthesis, by linear combination. We go back, right? And then from here, we have Ps. Okay? And then we take the C coordinate, right? So here is the inverse, right? The inverse. And here is T. And what is C? So we go from here to here. And so the composition, okay. So we establish a linear transformation from Rn to Rm. Okay? So the matrix representation of the linear transformation right? It's just since we just established that dx c here is equal to okay. Okay, so similarly, okay. So the matrix. Right, so the measure representation of the linear transformation. It's just right, so we know that. Now, the final thing. So this is the coordinate system, the change of coordinate. So I think from here, B to, so I keep track. And then go to V. And then go to W, E, and then go to C, and change the coordinate. Okay. So we go to X. Go to here, go to So the whole process, we know that this is the representation. We already know this is from go to here. So this is the C numbers here. So we have this one here. Okay, so now the representation is that so to do that, so we start with that. The Tx from right by doing the C from okay. And TXC, but TXC is the T transformation of B and C X. Okay. Relative to the basis B and C. Now, and the B coordinate is from and this must be equal to so now we conclude that the matrix representation of the linear transformation T relative to the basis B prime for V, C prime for W, right, becomes to a multiplication of three matrices. Okay, so let's see. So it's easy to read. First of all, we have a vector in the B coordinate, B prime coordinate. So we do the coordinate change to the B coordinate vector. And now every vector in the domain B is now in the B coordinate system. So we use the matrix representation of the linear transformation relative to the B coordinate system in B and C coordinate system for W. So now the result is the image in W under the C coordinate system. And then we do the coordinate change, right? From the C coordinate system to the C prime coordinate system. And this is exactly what we want to do. Okay, so we do coordinate change in the domain. All right, and we use the matrix representation for B and C. Now in the coordinate, we do the coordinate change from C to C. So this is what we have here. Everything. No, not different. Because it's the metric representation of relative to a basis B for B for domain and a basis C for domain. So it is for the linear transformation T. Okay, but this is nothing to do with any linear transformation. It's just the coordinate system change in the domain, only for the domain. So this is inside for the domain V. And this is the internal action for the domain, for the codomain W. So we just do the coordinate change for vectors in the codomain W. Because our question is, I want to know the relation between this one and this one, right? I want to know what is the relation between these two different metric representations. Because for the same linear transformation T from V to W, we have many different metric representations. It just means depends on the coordinate system B you choose for V, depends on the coordinate system C you choose for W. This is very important. So when you change the coordinate systems, you will change the metric representation. So my question is, how do we relate these two different metric representations? And this is the relation we established here. Okay? So we can turn this metric representation into this metric representation by what? By multiplying the transition matrix for coordinate change in V, and also by multiplying the transition matrix for coordinate change. And you have to check the dimension. Let me check the dimension of the matrix here. What is the dimension of this matrix? This is n times n. What is the metric representation here? This is n times n. And what is this coordinate change? This transition matrix for coordinate change? This is m times n. So m times n, m times n, n times n. So the dimension match to each other. And finally, this is m times 4. Okay, so this is one of the key results in linear algebra, and I just completed. A little bit sophisticated, but that's why I use the notation for you to memorize it easily, because I need that notation to help myself. Okay, and everything is just about the linear transformation. Okay, so the diagram you can compose different diagram as you wish. Okay? Any questions? Okay, so this is the original version. And so on Friday, I will specialize this representation into special cases where the V and the W are the same. This is very special, very important cases we will discuss on Friday. But I ask you to review the material I discussed today because this is the most general cases we can have. Right? We can have. And I hope you grab the key ideas here. Because all the material here is very important for the rest of the chapter 5 and chapter 6 when we talking about eigensystems. So I don't want you to get lost. So you have to know the material. Okay, so let's just take 4 minutes to